Okay, what we've got here is a standard normal distribution. That is a normal distribution with specifically a mean of 0 and a variance of 1. And let's be clear, when I say mean of 0, we could write this as expected value of z is equal to 0, because that's where it is. And this thing here is the variance of z is equal to 1. Z is continuous, so here is what it looks like. Can go off down there to minus infinity. This is the z-axis along here, all the way to plus infinity. And what it looks like is it's symmetrically distributed around 0. Where does this come from? Because this is the function. It's here. This is the function. So putting various values of z into here for a mean of 0 and a variance of 1. So that should disappear because it's variance of 1, i.e. sigma is equal to 1. Putting various values z into here, I'm going to end up with this shape. So plug in the various values and plot z versus f. Z, not x. Like so. Right, is everything else right? Yes. Right, so nobody here to tell me what I've done wrong. Alright, no, that's correct. I want to show that the MGF is this guy here. Yeah, that's correct. And that's for all t. So let's start. Start with a definition. M of t is equal to expected value of e to the tx. That's what you always have to remember. It's the starting ground. Just like for the Poisson one now, example I did earlier, we evaluate this thing. But since I made a mistake, expected value of e to t times the random variable. My random variable, I'm not calling it x, I'm calling it z. So that's something I'm glad I did that, because I guess students do that as well. Alright, so it's whatever you named your random variable, it's not always x. In this case I've called it z, so there you go. Put z up there. Because z is continuous, I have to integrate this function here times the PDF, i.e. f of x, and that's something that I just wrote earlier. So let's just substitute that right in. Pi e to the minus a half z squared, and this is the numerator, let's be clear, dz, of the possible values of z. But we know the possible values of z, because it's continuous, it goes from minus infinity to plus infinity because of the picture I showed you, where z runs from minus infinity to plus infinity. Alright, so what do I do with this? Don't be I'm kind of intimidated. It looks a terrible thing, and we don't like to do integration, but I'll show you that we do not need to do integration at all with this. Okay, so how to do it? Well, look at this guy, look at this guy. They both involve z's. So what is the point? The point is, just like the Poisson, we need to kind of just recognize something, that this normal is of the form integrate something, right? But I'm more interested in up here. So let's say it's some kind of constant. I'm not really interested in because it doesn't depend on z. E to the minus a half, and then something squared. In this case, it's z squared. All right, dz, and that must come to 1 over all possible values of z. So the question is, can I reorganize this thing so that it's of something squared? Because if I can, then this says that it integrates to 1. Let me show you what I mean. So just look into what they call this, some terminology here now, some math terminology. This thing's called the integrand, is what we're kind of integrating. Okay. So let's just isolate these two. So let's just say now, and also it's a good thing when we're doing these kind of proofs, let's give this let's give this a name, because we'll have to let's call this whole equation star, right? So we'll have to kind of refer back to it later, or tell the reader to look up there. Now, so I'm just looking here, e to the zt, or dz, times e to the minus a half z squared is equal to the e to the minus a half z squared minus 2zt. Let's call this double star. And so I want to focus on this guy here, because the whole thing is, can I write this with a square here? So something with a square. So if we look at it, z squared minus 2zt, what are you thinking? This almost looks like a quadratic function. Yeah, you usually use x squared plus bx plus some kind of constant. So we're lacking constant here. But we can complete the square here directly. Z, again, I made a video on completing the square if you're rusty with that. Z minus choice of t, because there's two lots of t's here, tz's, squared. So if you multiply that, you're going to have z squared, which is that term, and you're going to have minus 2zt, yes, which is that term, and then you're going to have plus t squared. Well, we have to compensate, because we have plus t squared, we have minus t squared. Now then the right hand side now is equal to the left hand side. So what's the point of doing that? Let's call this 3 stars. Well, if you substitute, this is what I mean by showing working now, 3 stars into 2 stars, you can see that this thing now is the form we want. We have e to the minus a half of, put in big bracket, z minus t squared minus t squared. And what you're saying to yourself is, so what, that's not exactly squared because I haven't got a squared on the outer term. Well, what I've done, and this is kind of more important, not only do we want to put a squared on the term what we're looking at, we want to separate out the z's and want to separate out the z term and the terms which do not depend on z. So here first block depends on z. That's z minus t squared. And then I have another term, minus is a plus, plus a half t squared. So I've separated it now, the z term from the t term. Doesn't matter that there's a t here. So that long as this thing looks like this thing, I is something squared. That is something squared which depends on z, which I'm integrating over. Now I'm running out of stars here. I don't know why I use stars. So what do I want to do? I want to now, exactly, I'm almost done now, because all I want to do is take this guy here, take this guy here, and I'm going to substitute it back into star. So the whole story, remember, I just started, pluck this guy, and I plucked this guy out, and that's where I got down here. And whiffle waffle, I've just got to expression where this is the equivalent of saying this. Yep. 3 stars into, hang on, this 3 stars into 2 stars, yep. Okay, so I substitute now into star, so let's say, I'm running out of stars, so let's say 4 stars. 4 stars back into stars, and I have that mt, because let's be clear that it's mt I'm after, let's not lose sight of that fact, is equal to square root of 2 pi, and then times this thing here, let's just write down as it is, minus a half. Of course, you don't have to write all these steps down, I'm just trying to do it, put as many steps as I think I need. There you go. And I'm integrating over z, don't forget. But, this is a nice bit, as before you're integrating over z. So anything that does not depend on z, you pull it out. Well, that's a constant, I can pull it out, but I don't want it as a constant. And that depends on z, I cannot pull it out. That's a constant, it does not depend on z. I can pull it out, so I take it out. And as we're going along, you can kind of see, because I gave you the answer already, that's the term I'm after. integrate 2 pi e to the minus a half z minus t squared over dz. Now, would you believe it if I told you that this thing is going to integrate to 1 because it's a normal distribution with a variance of 1 and a mean of t. If you can't see that because you haven't got the PDF of a general normal, just recognize that it's of the form that I want. It's some kind of normalizing constant times e to the minus a half times a lump of something squared, where that lump involves the z. And here it does. So I can say that this whole thing, it integrates, it comes to 1, so I don't actually have to do any integration. And so I'm done. Equals e to the half t squared, and that thing is all t in the real line because you're not dividing by 0 at any point there. So what I was going to do in class is to actually work this out for the class which I've just done, and then ask them to do this other problem. Show then more generally that if x is normal distribution with a mean of mu, the variance of sigma square, so you've seen that I've generalized it completely now, not a mean of 0 but a mean of mu, the variance of sigma square not being a variance of 1 like I've used, that now the MGF looks like this: e to the mu of t plus half mu squared t square. Show this. You'd be using exactly the same method as I just shown you. So that's something that you want to try. I might put up the video for that at a later date, but I always like students to have a try. It's the same method, and if you can work yourself through this, then you've understood what I've done. Just to recap how you do it: you write down the formula. Write down the formula for the MGF, put in the PDF, and then the idea is to use completing the square to separate out in the exponential term something that does not depend on x with something that does depend on x, and the thing that depends on x is going to be squared, and hence you've got some kind of normal, and that which will integrate to 1. As always, we've got the MGF, so watch, well, we can use it to compute moments. So let's just show that we can do that. Let's just do the first couple of moments. The first moment, e to the x, we know is first derivative of m with respect to t. How we're going to differentiate this thing? Chain rule. So consider e to the half u, where u is equal, no, not even have that, e to the u, can we bring that u closer? Consider e to the u, i.e. let e to the u equals e to the half t square, this MGF, where u is equal to the half t square. Then we know that if I do this derivative of mt, that will be using the chain rule, dm, let's call this whole block m, by du dot du by dt. And so what do we have? Dm by du is eu. Du by dt, that's bring down the 2's cancel with the half, so you got t. Substitute back for the u, that's e to the half t square times t. Therefore, we can say that this first moment, which is equal first derivative of the moment generating function evaluated at 0, plug in zeros for here, e to the power of 0 is 1 times 0, 0, which is what you'd expect, because we already said that z is normal, mean of 0 and variance 1. Okay, yeah, and just in case anybody kind of points out to me in a video, yes, I've certainly gone to using x. I have kind of a liking for x, so I use it all the time. No, we're working with z's, remember? Right at the start I told you we're working with z's, so where else is z? Okay. First thing. Next thing, variance. So for that I need the second moment as well. The second moment of z squared is going to be the second derivative of the moment generating function evaluated at 0. But we already found the first derivative. The first derivative is this. So I have to differentiate again. How? This time that's a t dot another t, so that's a product rule, isn't it? So differentiate, let's write down this thing, differentiate this thing, write down t, differentiate that thing, but this thing is, we've already done it in the first step, so we just kind of write it down. E to the half, to get the first moment that was. E dot t, remember this expression? We did that from here. Plus, and then now write this thing, half t squared, and differentiate this guy, so that's 1 dot 1. Therefore, second moment, ex squared, which is equal to the second derivative evaluated at 0, is equal, plug in t is 0, that whole thing goes to 0, because at 0 times something that's finite, it's going to be 0, plus e to the 0 here is 1 times 1, 1. Don't stop there, because I know like you might automatically just stop there, and God, why have I done it again? Well, z, right? Okay. Well, I've not got any excuses really, but at least I've spotted it. Okay, therefore, variance of, wait for it, z, yes, is equal to the second moment of, let's not therefore, this is true anyway. So, since variance of z is equal to the second moment of z minus the first moment of z all squared, we can plug those in now. I'm running out of paper as well, so it's good we're finishing. E first moment squared is 1 minus the second moment, sorry, which is 1 because I've just done it. First moment was 0, all squared, it's going to be 0 obviously. There, finished. So I've shown that using the MGF that the variance of z is 1. Phew. Okay, so that's it.